Good afternoon, everyone, and welcome to MOS Live Ask a Scientist. In just a few moments, we are going to be meeting our educators who will answer all of your questions related to electromagnetism. My name is Christina. I'll be serving as your moderator today, and although you can see my face right now, you'll mostly be hearing my voice in the background as I share your observations and questions with our educators. If you are watching on Zoom today and you would like to ask a question, you can do so by clicking on the Q&A button at the bottom of your screen. And don't forget to include your name and age if you would like a shout out. If you need captions, you can get those by selecting Show Captions on the Close Caption button at the bottom of your screen. If you happen to be watching on YouTube or Facebook Live, we're so happy to have you with us today. Unfortunately, we will not be able to see your questions and observations, but we do hope you enjoy the show. But with all of that being said, I would like to invite our educators to turn on their camera, introduce themselves, and they're going to be sharing their favorite use of electromagnetism.
Hello, my name is Chuck. I use he, him, and his pronouns. And I think the coolest application or aspect, if you will, of electromagnetism is something you can see going on behind me now, and that is the Aurora Borealis, which those of you in the United States might get to see some of in the actual night sky tonight.
Hi, everyone. My name is Eric. My pronouns are he, him, and I really like talking about superconductors when we are mentioning electromagnetism, material that lets electricity pass through it perfectly, and that creates really strange magnetic effects, including being able to hover a magnet above a superconductor and being able to imagine things like trains that hover off their tracks and zoom along without any friction. We can actually build those.
Hi, everybody. Good afternoon. My name is Karen. My favorite sort of use of electromagnets is in junkyards. So if you imagine needing to move very large vehicles around a junkyard, they take these immense magnets that they create using electricity, hover it down, it sucks up the vehicle, and then they can move it around that junkyard to wherever they need it to be, since these cars and trucks likely do not run anymore.
Those are all super cool applications. Thank you for sharing, educators. And to get us started, I thought we could actually start with just talking about what is electromagnetism.
Always a good place to start. So there's actually a lot of different aspects, and I think we can each probably touch upon some of them. When I'm thinking about electromagnetism, one of the things I consider is the interaction between the electric force and the magnetic force. So if you've ever heard that word force, we often think of it in terms of, say, the force of gravity. Forces are invisible. You don't see them, but they're all around us all the time. And what's really interesting is the electric force, which we typically think of in terms of electricity and things like that, and the magnetic force are actually connected. If you have one, you have the other. You have the first, you have the other. So it's a really interesting interaction that you can utilize in a lot of different ways. For instance, you can make giant electromagnets or tiny electromagnets to move things around if you don't have a permanent magnet on hand. You can also use it to stay safe in the middle of a lightning storm. Sort of this interaction between electricity and magnetism is what keeps you safe in a car or in a bus or in an airplane. So that's sort of what I think of when I consider electromagnetism. I don't know if Chuck or Eric want to add anything to that definition.
Sure. Every time you use your phone or speak into a microphone, for example, or use an electrical transformer, even the Tesla coils we have at the museum, that is all about electromagnetism. Think about how I'm speaking right now into this, I don't know if you can see it, this microphone. Inside the microphone, my voice is moving a cone or something, moving a surface back and forth. Attached to that is a magnet. And that magnet, because of the sound, the pressure of my sound waves, as I'm talking into the magnet, moves a magnet back and forth through a coil of wire. And one of the neat things about electromagnetism is that a moving magnetic field, as that magnet moves back and forth, it generates an electric current in the wire. And that electric current can then be sent over long distances. And then when it gets to its source, then that electric current will move a magnet back and forth in the same way that my voice moved the magnet back and forth in the microphone. In this case, it's happening in a speaker, and then it can move the speaker in a way that makes sound waves. That's how a telephone works. That's how sound systems work. And it's all a neat example of electromagnetism in action.
And something you might hear us mention a few times during this show is an electric or magnetic field. And a field in science is really just kind of a range of data. And so if you think about a map of the United States, putting temperatures on every big city, that's a field of data because every location has a different value. And so you might be able to look at that data and see that it's colder in the Northeast and it's hotter in the southern part of the country. And electric and magnetic fields work the same way, except they have both a value and a direction. So it's actually something more like mapping the wind speed at every point across, say, the state of Massachusetts to see where the wind is strongest, where every point not only has a value of how fast the wind is blowing, but a direction of which way. And so you could imagine looking at a map of Massachusetts and seeing lots of long lines on one side pointing to the north, meaning there's a strong wind blowing that way. And on the other part of the state, maybe there's some smaller lines pointing south, meaning the wind is gentler and blowing the other way. So for electric and magnetic field, it's the same thing. When we're talking about generating an electric field, that means that along a piece of wire or surrounding something, there might be electric forces pushing or pulling in different directions. They have different values, how strong that push is. And they also have different directions, which way they're pushing. So when we're talking about creating a magnetic field or changing it to get a current, all those, what we're talking about is the value, how strong it is, and the direction that it's pointing.
If you guys maybe in school, either currently or in the past, have studied electromagnetism, you may have heard something called the electromagnetic spectrum, because when we talk about it, what we're really talking about is waves. Some waves that are visible in the form of visible light, and some waves that are invisible to the human eye, either really small wavelengths, so teeny tiny ones. Those are the ones that you can see sort of in the purpley side of the spectrum here in this picture, or the much wider wave. So things maybe you've heard of like infrared or radio waves. These are just some examples of their lengths. So like what Chuck was talking about, the way moving the magnets through the electric wires in order to make the sound. You can also think about radio waves. As that radio tower is sending out these invisible to the human eye electromagnetic waves, it's what's making your cell phone work or your radio tune into that exact station. And if you've ever been listening to a radio station and maybe sitting in a car or driving in a car or on a train, as you get further away from that radio signal, that radio tower, it starts getting a little bit more staticky because those waves can only travel such a distance. They're not infinite in how far they can travel. So those larger waves that are the size of soccer fields or houses, they don't harm the human body. Sometimes when you get to those shorter wavelengths over in the, again, the purpley side, the gamma rays, X-rays are pretty cool. They allow us to see the bones inside of our body, but you certainly wouldn't want to have 800 X-rays a day because that could actually affect the cells of your body itself. So just for a little bit more background of how wide a topic when we're thinking about electromagnetism is, it has to do with the electric force, the magnetic force, but also what we would consider light waves in this electromagnetic spectrum.
That's all really fascinating. It sounds like a really great way to start this conversation today. So thank you all. We have a question asking about that terminology electromagnetism and how it's a combination of electricity and magnetism. Is it possible to have one without the other?
No, maybe negligible. They do go hand in hand.
Yeah, in a sense, you can have electricity really coming from electric charges, which are tiny, invisible, and they make up everything. So everything around you, your house, your hair, the air itself, it all has electric charges in it. And when you think of what we call static electricity, when you are rubbing your feet along the carpet and you touch something and you get a shock, that we call static electricity. Static meaning not moving. It's really only static before you get that shock, meaning it's not moving until it jumps to your finger and shocks you. But in that moment of the shock, you have moving electric charges, that's the current. And anytime you have a current changing, you're generating a magnetic field. So even in that tiny little shock, you get a magnetic force as well. So really, they always do go hand in hand.
And that's very good for us, those of us who do theater of electricity demonstrations at the museum. Maybe you're wondering why it is that somebody can be in that cage and lift themselves up and have the cage struck by a 1,000,000-volt lightning bolt and be safe. And that has to do with magnetism as well. It turns out that there is a repulsive force, the kind of electricity that comes all at once in a spark coming down and hitting that cage. When what that is a very rapidly changing electric field. It goes from 0 to hundreds or thousands of amperes or even millions of amperes in a very tiny fraction of a second, and then back to 0 again. That change in the electric field causes a magnetic response. It causes a magnetic field that actually repels the electric charge to the outside of the cage. So the operator can touch the inside of the cage even, and all the electricity is on the outside of the cage. And so you get it's safe. It's something called the Faraday effect. So that's something that keeps you safe in a lightning storm inside your metal car or any other enclosing metal object like we have at the Museum of Science with the cage.
And hopefully our visitors will be able to see that one day again. And I know, Eric, you had mentioned a term earlier of superconductors, and I was wondering if you could explain to us what that is.
So a conductor is something that lets electric charges pass through it very easily. Typically, we think of things like metal. So our wires in our walls that bring us electricity throughout our house are a good conductor. They're made of copper. Copper lets electric charges pass through it very easily. A superconductor lets charges pass through it not just very, very easily, but perfectly. So without any loss at all, without any opposition. And so that's very useful when we're designing things like supercomputers, but also it has some really cool effects when you do things like place a magnet near a superconductor. Because what happens is all of the magnetic field lines from that magnet get pushed outside of the superconductor. And so it just creates this stable point where you can take a magnet and place it on top of the superconductor. It will hover up above, and the magnetic forces that the superconductor is giving off are balancing gravity, and it's changing. No matter which way the magnet moves or falls, it always is balanced on there. Now, superconductors typically only work at extremely cold temperatures. So if you've seen one at the Museum of Science, it's probably in a demonstration where we're also using liquid nitrogen, something that we can use to cool objects down by hundreds of degrees in a matter of seconds. So we make that superconductor extremely cold, where it turns on and becomes a superconductor instead of an ordinary piece of ceramic. And then we can see this effect. And then as we wait, we can actually watch as the magnet starts to slowly fall down, and then the effect turns off and the magnet falls back down. So
that's why researchers, sorry, I was just gonna say, are working really hard to figure out, can we come up with materials that will have these really amazing superconducting abilities at much higher temperatures? There were some superconducting trains, Eric mentioned that briefly at the beginning, in the past in areas of Europe. But honestly, I think trying to keep tracks or the magnets, I don't know exactly sort of the mechanisms of how that worked, but trying to keep the super cooled, I think just got too expensive, too dangerous, however it might be. So there's a lot of research going into, can we create these amazing levitating properties at sort of more normal temperatures that we would come across in our day-to-day.
And we have a clarifying question coming in now that might be related to the little graph you showed us earlier, Karen. But Isora Hamasaki, 9 years old, would like to know, what do we do with electromagnetism?
Well, we do lots of things with magnets. We do lots of things with electricity, and electricity and magnetism can be viewed as different aspects of the same problem. Now, electromagnetic energy are the light waves that Karen was talking about, and also infrared and ultraviolet and so forth. One of the neat ways that I, with my background in astronomy, think of when I think of electromagnetism is it enables us to find out more about the universe. Our eyes can see visible light, and that's one type of electromagnetic radiation. Anything that is of a certain temperature, and everything is a certain temperature above absolute zero, emits electromagnetic radiation if it has a heat source inside it. For example, the sun emits lots of electromagnetic radiation, other stars do, and that comes out and it's everywhere, propagates through the whole universe, and we can see it as different types of light. Not only the visible light that our eyes can see, but also the infrared, the electromagnetic, X-rays, gamma rays, and so forth. The hotter something is, the more energy it has, the more high energy radiation it emits, such as X-rays and gamma rays. We can use those to find out what's going on in the insides of stars, for example. We can use those to find out, to see through dense clouds of gas, to see regions where stars are being born. We can see deeper into things, and not to mention all of the myriad uses we've been talking about, like how you talk on the telephone, how you use a loudspeaker, sound system, and others that I'm sure my other panelists can talk more about too.
Watching TV, getting those X-rays if you maybe broke a bone, or people who are in certain treatments for, say, cancer might be getting radiation, which is just another wavelength of the electromagnetic spectrum. Also, myself, I had a really severe concussion last year, and I had a whole lot of scans on my brain. We're using this type of radiation or this type of electromagnetic waves in order to see what the inside of my brain looked like, which was really awesome to see. Output pictures, I'm not going to lie, as a science nerd, I enjoyed that.
It sounds like we have had some amazing uses of electromagnetism, so thank you for those examples. And our next question is more of a terminology question, understanding the difference between electric current and then voltage, which you often see on a lot of equipment, maybe in home or outside.
Yeah, so at the most basic, so Eric briefly mentioned electrical charges. You've probably heard of positive charge and negative charge. And when those negative charges start moving, or at least the energy of those charges starts moving, we call that the current, and it's measured in amperes. If you've ever looked at something that it says it has X number of amps, it's just sort of the shorthand for amperes. And it's literally like the number of charges that energy is coming from, where the voltage, I like to use the technical term, it's the oomph behind it. So how much energy is it moving through? So Chuck was mentioning that our giant Van de Graaff generator at the Museum of Science will shoot up upwards of 1,000,000 volts. So there's a lot of push. There's actually a really incredibly small amperage. It's only, I don't know, I don't even know if we can measure the number of individual charges that are moving through the air to create our lightning bolts. But that's where you end up, it's a better understanding of what we would call power. So if something has a very high voltage, a relatively low amperage, it's not very powerful. If something has a very high amperage and a very high voltage, that is a much more powerful sort of energetic output of whatever you might be talking about.
Excellent. And I think we have a series here of kind of safety questions or maybe concerns about electricity. So thinking about electric shocks, someone here is asking, why is it that a shock from something like a 12-volt battery not be as dangerous as a shock from a 12-volt car battery?
The difference is in the current, the amount of current, because electricity is not just voltage, which is how hard a push the electricity is getting, the electrical charged particles, but the current, how many of them are that are getting pushed along your wire. In a car battery, the current is a lot greater than it is in the 9-volt or 12-volt regular battery. That is actually dangerous. It's enough to stop your heart. So you have to consider not only the voltage, but the current as well.
And thinking about when you're outside and you see those telephone, not telephone, but or maybe telephone poles with the lights on them, and there's often this like round, almost looks kind of like a garbage can attached to the top of it. Do you all know what those are and why do we have them?
Yeah, so those are transformers, and you might see them up on those telephone poles. You might see them in the city, just kind of sitting on the sidewalk, kind of like a big box. And it might be emitting kind of a humming noise. And what those are doing is taking electrical charges that are moving through the wires and then reducing their voltage. So what we can do is actually, without even touching the wires together, use the moving electric charges to influence other moving electric charges in another wire without actually connecting them. And that's happening because there's magnetic forces. So here we have electricity and magnetism going back and forth again. We can have our power plants generate very high voltage electric current and send it through wires out to neighborhoods. And then as it splits and spreads out, once it gets closer to your house, you don't want that really high voltage. You want a much lower voltage that actually is harder to travel over a greater distance. So it only has to go from, say, the telephone pole down the street to your house. So we use that transformer to take really high voltage down to a much lower voltage to go in and power our actual electronics inside of our house.
And thinking about electronics inside of our house, we have a question about the actual sockets. And why is it that they have that sort of third circular point in the bottom of it?
Grounding spot. Basically, it makes it safer. I actually don't know all the inner workings of like 3-phase electrical currents that are in our outlets versus 2-phase. But essentially having that grounding pin is a safer way of powering electronics. So you might notice like your lamps, your clock radios, maybe even your computers might only just have those 2 prongs. It has to do with, I believe, sort of how powerful that particular electronic is. So something like your refrigerator is definitely going to have that grounding wire or grounding pin in the outlet, where the other sort of your more common things like your lamp in your bedroom isn't powerful enough to really need that. And maybe Chuck or Eric can explain that a little bit better, because I feel like I may have muffed it up a bit.
Well, grounding is important. Yeah. Grounding is important. Yeah.
Go ahead, Chuck.
Yeah, grounding is important because if you have a grounding is connected to the earth, that third pin is through some way connected to the earth, and if you connect something to that, then you will dissipate its electric charge. It won't have a static charge. Sometimes electrical components have a tendency to build up a static charge if electricity is going through them for long periods of time, and especially with sensitive electronic components, you don't want a static charge in the wiring or anywhere on the outside of that electronic piece. So it helps to have a connection that connects to ground to dissipate any static charge that builds up on it.
And thinking about the United States and how that might compare to other countries, do you all know why it is that the outlets in the US look different than other countries? And would they also have these grounding pins? And why is their current a little bit different? And why do they do things differently than we do?
If you've ever traveled to other countries and brought your laptop, you need to bring an adapter, because other countries have different looking outlets. They might have a different voltage. They might have a different current. And also there's something called the frequency, which means how fast the alternating current shifts. So we have a lightning bolt or a spark that you touch something and you get a little shock. That's direct current. That's electric charges flowing in one direction from one spot to another. The lightning bolt has charges in the ground, charges in the clouds going straight down to the ground. What we have in our outlets is alternating current, which means instead of it making one complete circuit, it just gets pushed back and forth over and over. And that happens really, really fast. In our outlets, it happens 60 times every second. But in other places around the world, they might have it be slightly different, maybe only 50 or maybe 70. So it really just depends on how the power plants in that country are set up, what kind of voltage and current and frequency you're getting in your house, what comes from the power plant to your house. And turns out there's not a standard, just like there's not standards in a lot of other things, like how to connect a piece of electronics to your computer. There's a lot of different cords that can do that. So it would be great if you could just go anywhere in the world and plug something in, but since it's not standardized, there's a couple different ways to do that.
And maybe one day when we can travel again, we can see what you mean in person, Eric. And I think we're going to end with one last question today, and it's specifically about lightning, since that's come up a few times during our program today. And specifically, is lightning an example of electricity? And when you see it outside, how can you keep yourself safe from it?
Well, lightning, we see lightning, you think, that's electricity. Well, lightning itself is not electricity, but it is an effect of electricity. When when that tremendous concentration of negative charge builds up in the bottom of a thundercloud, attracts a whole bunch of positive charge in the earth that wants to get to the negative charge because opposites attract each other, makes a wire out of the air. So that's basically a large amount of current of charged particles flowing from one place to the other. When that happens, when that tremendous amount of current driven by a tremendous push, a tremendous amount of voltage, travels through the air, it rubs up against the air and makes it glow white hot at a temperature of about 90,000 degrees. And basically, it's only for a fraction of a second, but it is a very strong effect of electricity, and it creates that energy is going to be dissipated as light. It's dissipated as a sound wave when the air expands because it's been heated so much. And so it's an example of electricity producing a whole lot of other effects as it releases energy.
There's a bunch of ways to keep yourself safe in the midst of a lightning storm. The most important, or the easiest and best thing you can do, is be inside of a sort of modern building. Eric mentioned those wires moving through our walls. Even if the building you were in were to get struck by the lightning bolt, which is a pretty small percentage of buildings that get struck, but that electrical energy would move through the metal wires and the metal pipes in our walls and not injure you. Now, if you happen to be stuck outside, you want to take this one, Eric? How do you stay safe?
So if you can't get to a building, cars are also safe because you're surrounded by metal on all sides, which is a good conductor. And like Chuck mentioned, inside of our theater of electricity, it tends to flow on the outside of a conductor because of those magnetic forces that happen in a split second. If you can't get there, then the best thing to do is just to get as low as you can, find a ditch or a lower area, stay away from trees or anything tall. They're more likely to get struck by lightning. And you can kind of get as low as you can. Don't lay on the ground because lightning can strike the ground and travel sideways and then up through you. So kind of crouch down as low as you can, up on the balls of your feet, and hope that lightning storm passes. But overall, don't get yourself in that situation. Check the weather, know what it's going to be like if there's a chance of thunderstorms before you go on a hike or you go out on a long fishing trip. And if you start to hear thunder, don't wait until you see lightning. Get somewhere safe right away.
When thunder roars, go indoors.
Oh, very good points, and a great little expression to remember as our last thing here today. I am looking at our time, and we're just about out of it. So I want to thank Karen, Eric, and Chuck for being such wonderful educators today. You can say goodbye to our audience.
Everyone.
Bye, everyone.
Bye-bye.
And I want to thank our audience today for asking so many great questions. If we didn't get to your question today, I am sorry, but what I can say is that we are going to be doing more programs like these, and you'll have more opportunities to ask additional questions. You can check out all of our offerings by visiting our website at mos.org/MOS at home. And if you enjoyed the program today and would like to learn more about how you can support the Museum of Science, you can do that by visiting our website at engage.mos.org. We hope you enjoyed the program, and we will catch you at the next one.